think I can think of a tangent of 47 degrees. It's nothing more than the tangent of 45 degrees plus 2 degrees. I only chose 45 degrees because it's an angle with which I'm familiar in terms of my tangent functions. I'm lazy. Just like over there, I rewrote 51 as 4 to 9 plus something because I'm familiar with this square rooting function of value of 49. So, you guys, let's play. I think this is nothing more than the tangent of 45 degrees, increased by a small change in the y direction. I'm just too tired and too lazy to compute the small change in the y direction. I refuse. So I will use differentials and approximate the output of the tangent of 45 with delta y with this mathematical beast right here, which I can now interpret as nothing more than the tangent of 45 degrees, plus my f prime evaluated at 45 degrees times a small change in the x direction. It's just as it differentiates the tangent of anything, what the heck do you get? I said, to differentiate the tangent of anything, what the heck do you get?
Secant square root of that.
The secant square root of that thing. And by the way, dx is...
2.
Oh shoot, I'm running out of room. Oh, does that, bless you, does that give me the tangent of 45 degrees? Which, by the way, is nothing more than...
1. Yes.
Plus, well, the cosine of 45 degrees is 1 over root 2. So the secant would be the reciprocal, which is root 2. Oh, but I'm squaring it, so I guess I'm positive 2.
Times 2 is 4.
Times the 2 is going to give me... I can't hear you.
6.
I can't hear you.
Nothing is 2 degrees.
Thank you, nothing. It's not a number. So to convert degrees to radians, what do you do?
Multiply by pi over...
Multiply by pi over 180. But that means I have 2 degrees, nothing more than pi over 90. Are you guys there? Do you remember that? Really? I'm a mathematician. I never remember it.
I remember that we have formula for it. I just derive it in my head. So
That's what I do too. Think about this. 1 full half revolution in degrees, isn't that just 180 degrees?
Yes.
But one full half revolution in radian measures is going to be pi. Doesn't that necessarily imply if I divide both sides by 180 that 1 degrees is nothing more than pi over 180? Just be lazy. Now if I multiply both sides by 2, I get 2 degrees is equal to pi over 90. Yeah, just be lazy. You don't have to remember anything. Oh, by the way, that gives me a 1 plus pi over 45. But this gives me approximately, I don't know, I didn't bring my calculator. Nobody's going to beat me to this.
Oh, I got this.
I'm so happy.
Okay, 1.0698137.
However, if you are on your calculator, make sure it's in degree mode.
It is in degree mode.
What would you get for the tangent of 47 degrees?
Tangent of 47 degrees, we get 1.072368871.
That's pretty darn close, isn't it? I'm only deviating the hundredths place in the second decimal position. That's not bad.
It's a cool party trick and all, but why would we?
You ever
Yeah.
stuck on a deserted island?
Yeah, if you're stuck on a deserted island, you got no calculator, and you're dying to come with a tangent of 47 degrees, this works out beautifully. Just do it in the sand.
And your stick breaks.
Stick breaks.
Find more.
Now, you guys, the downside to this technique the downside to it is this. What if I don't know the tangent of 47 degrees? Question, how accurate is that?
Pretty dark.
Actually, you don't know. I mean, you really don't know. And so in mathematics, particularly applied mathematics, we typically don't like to use approximation techniques unless we know in advance how accurate they're going to be. And I have to confess, I can't tell you how accurate it's going to be in a general setting using this new method I call Newton's method of approximation. However, if you guys just give me a little bit of time when I give you some better techniques for approximating things like the square root of 49 or 51, I mean.
Is that what this is?
This is
Newton's method?
Newton's method of approximation.
I like how he started.
He started what?
Interesting how the book doesn't give Newton any credit for it.
What was that?
this chapter
Stuart-
4.5?
Oh, you know what?
Yeah.
He probably gives us title to something else in the book.
No.
He probably calls something else in the method approximation. For now, we'll just call it differentials. Oh, I didn't mean to erase it, you guys. So, you guys, let me do something different. Do you guys agree this is the equation of a line in general? Do you agree that this is the equation of a tangent line to the graph of f at x equals a? I lost it, sorry. And if I were to add f of a to both sides, wouldn't I get this? But that being the case, are these the y values in the graph of my function f? Are they?
Yes.
Are they really?
Yeah.
See, I think they're not. I think these are the y values in the graph of my tangent line. So technically speaking, if you were to use everything above this brace to approximate the output of my function f at different values of x locally near x equals a, then I think this y value is just a linear approximation for my function. Oh shoot, you guys, did I just mess up royally? Did I just completely change the name of the game? I think definitely not. Think about it. Over here, wasn't I merely trying to approximate the output of my function f? When x is equal to, hold it, I messed up. This thing right here. And you and I realized this is nothing more than my function f eval at a increased by f prime of a times a small change in the x direction. But you look at my linear approximation. I think it says the same darn thing. Here's my L of x. As a matter of fact, I think what you see inside the circle right here is nothing more than a small horizontal deviation from A by delta x units. But jeepers, isn't that what that is? That's just my delta x. It changed between a value of x close to A and A itself. I think it says the same darn thing.
So f prime of a times dx, that's the slope at the point times the distance, the approximate distance that it changed from left to right.
Thank you, from left to right. So dx represents a small deviation in the x direction.
And so, like, how does that slope times the x, like,
Give you a change in the
what
y
number
value.
does that? So that's the change in y value?
Yeah, do you see why?
No.
Because think about it. I think f prime of a is just a slope of a line. And if I've got a line like this, x-axis, y-axis, here's my line. To get from one point to another, I mean, what do? Don't you just travel a certain distance and multiply by the slope? And that'll give you the corresponding vertical deviation. Ooh, you didn't like that. Don't look at it. Let me try to do a better job. X-axis, y-axis. Here's a line. And the slope is just downward. Would you not agree that if I traveled horizontally this many units and vertically this many units, is it not true that the ratio of b to a is just a slope on a line? But if I multiply both sides by a, doesn't that tell me that my vertical deviation is just the slope times the horizontal deviation? It's just that when it comes to functions, not lines, I probably represent b, or my m, as f prime.
I've never looked at it in that sense of just finding like what b is by itself. I've always just seen the slope as rise over around it.
Yeah, but you're so sophisticated at this point, now it makes sense, doesn't it?
Right.
You can easily see it. So you guys humor me with this. What's the graph of that function look like? Guys, you can humor me. Okay, I like the movement, but we use vocabulary. Let's not be French. Let's not mime.
There's a vertical asymptote, you can see, right?
Yeah, but what's another name for the curve? I saw hyperbola. So your standard hyperbola with the asymptotes on the x and y axes. You guys there? Okay. that if I were to try to find the linear approximation, you guys, I just think it's goofy. It's nothing more than what I did here with differentials, just using different language. I think the output of my linear approximation is going to be nothing more than, just like with my differentials over there, the output of my function f at x equals a, plus my f prime of a times x minus a. It's just an a in this particular case is 1. Let's give it a shot. So I think my linear approximation is going to be my f evaluated a, plus my f prime evaluated a. Sorry, did I forget to put my a in, you guys? What is a?
1
Plus my f prime of a, which is nothing more than negative 1 over,
x squared.
yeah, my a squared, times my x minus a. And that's going to leave me with my linear approximation's output to be nothing more than, I have no idea. Is that a negative x plus 2? Oh, thank goodness it's a linear function. It's supposed to be. Again, it's a linear approximation. Graphically speaking, does it seem right? Graphically speaking, does it seem to make sense?
Yes.
Yeah, I think it does make a lot of sense. If here's my standard hyperbola, clearly there's a point on the graph, 1, 1. I think the tangent line should be the line that passed through the y-axis at 0, 2, and whose slope is negative 1. That's exactly what the line is.
Well, what
It
about
is
the
just a
one?
tangent line.
What about the tangent line of the rest of the graph on the negative side of them?
Ah, but you know what? I don't give a darn. I was just trying to find a linear approximation about x equals 1.
Oh, okay.
That was the question.
Okay, yeah.
So, when the question is saying about x equals 1, what is it saying? And why
You know,
did
it's
we
really
let
saying-
a be 1?
You know, I could have phrased it this way. I mean, this really does mean that a is equal to 1 in this equation. I just, in English, I tend to use this word about. When I'm trying to find some kind of approximation of my curve, locally speaking about that value of x. And you have to confess, if I ask for a linear approximation about x equals 2, I think here's where the point on the curve is at 2, 1/2. And I think the tangent line will have a less than slope. Well, I meant to say small and absolute values. I think it would be a different linear approximation.
So whenever the question says x equals some number, do we just say that a is equal to that number?
Yes, I agree completely. If you,
Wait, so is linear approximation another name for find the equation of the tangent line?
absolutely.
Oh, okay.
As a matter of fact, you guys, I'm sorry.
So if this is Newton's method, then what does that have to do with finding the zeros of an equation using tangent lines where they intersect the x?
Not yet. I'm not going to get there yet. I'm getting close to it.
I was trying to point out it's not even in this book.
You got to be kidding, really?
It's in the Stewart book, but it is definitely not in here.
You know, you guys, I have used this book for math at 30 once before. I just don't remember. So no Newton's method. Oh, don't you be like that. I'll give it to you anyways. I just need a little more time. So I'm really building up to Newton's method. I haven't really given it to you yet. You guys, I think I made a mistake. Can we just double check this real quick? I mean, this really is the equation of the tangent line at that particular value of x. I think the tangent line of the curve should agree at x equals 1. And when I plug 1 in for x here, I get y is equal to 1. We've already done that. But when I plug 1 in for x here, what do I get? 1. I agree. Now, the reason why I sometimes refer to this as a linearization for my function at x equals 1 is because if now I ask you for the y value when x is equal to 1.01, life might be a little difficult here. Because I got to divide 1 by 1.01. I don't want to, I'm too tired. What I could do instead is just divide my linearization at 1.01, and I think the arithmetic is a heck of a lot easier. I know the answer right off the top of my head. I think it's going to be 0. I'm slow. 99. 0.99, because I can do the arithmetic in my head. Do you guys see my point?
Yes.
It just makes evaluating a function easier, although you're really going to get an approximation for the evaluation of a function, and it's probably going to be pretty darn off unless you choose a value of x, locally speaking, about that particular choice for a. Okay. As long as you agree with that, as long as you see it. case,
Must be important.
that's right.
It's so sad. At least the lines are straight.
You guys, I know I can't draw very well, but relative to my picture, does it appear to be the case that f of a is equal to f of b?
It appears so.
Approximately.
Yes.
And I meant it to be. I meant it to be. Does it also seem clear that at least relative to how I drew my picture, does it seem reasonable that f is continuous?
Yes.
At least over this interval. Does it seem reasonable that f is differentiable
Yes. Yes.
over the corresponding open interval? But that being the case, you guys, what do you think you could say about the slope of the tangent line being equal to 0 anywhere between a and b? According to my picture, does there seem to be another value of x between a and b for which the tangent line is horizontal?
Yes.
Yeah.
Yeah, I do. As a matter of fact, I think there's a point, roughly speaking, right around here on the curve, whose x value is, I'm making up a letter out of thin air, for which the tangent line is horizontal. Now, personally, I think it's because these two conditions are being met, but I do think it's reasonable to look at the picture and proclaim that there should be a value of x between a and b called c, for which f prime of c is equal to 0. Now, I gotta confess, I can really mess this up. X-axis, y-axis. You know, if I think I've got a function y equals f of x that does not satisfy this criteria over here, then here's clearly a picture, you guys, I can draw for which between a and b, there's no value of c for which the tangent line is horizontal. Even if I lack the second criteria, differentiability, but I'm continuous everywhere. Like, for example, you take a peek at this picture. Here's an example where I've got a function f, which is not differentiable everywhere strictly between a and b, and therefore the conclusion of the result, namely that there's a value of x in between a and b for which the tangent line is horizontal, does not hold. However, if these three criteria are being met, I do think the conclusion is there's got to be a value for x, call it c, for which the tangent line is horizontal. This is so important, I'm going to give it a name. I'm going to refer to this as Rolle's theorem. It's a theorem.
Is that 2 L's?
It is 2 L's, yes. If f is continuous over this interval from a to b, and f is differentiable over the corresponding open interval, and f of a equals f of b, then it's got to be the case that there exists a value of x called a c strictly between a and b, such that f prime of c is equal to 0. That's the official statement of Rolle's theorem. Yes?
Do we have to know?
You know, I have to confess, Rolle's theorem really is a basis for me to be able to prove something more important called the mean value theorem. Regardless, this is important for further mathematical results. You guys, if you don't mind, I'm going to prove it. So you guys relax, and you just tell me if my argument's not clear. So proof. Actually, you know what? Can I do something different, you guys? Can I break this up into cases? I mean, suppose that f is a constant function. Can I stop? I mean, f is a constant function. That means that for all values of x in the interval from a to b, that f of x is is equal to a constant, so f prime of x is equal to 0. I think every value of x in that open interval is going to satisfy the conclusion of Rolle's theorem. So if you guys don't mind, I'll skip this part. It's that trivial. Let's suppose otherwise. Suppose f is not a constant function. And if that's the case, then without loss of generality, can I just suppose that f of x is strictly bigger than f of a for some value of x? In the interval from a to b. However, it is the case that I'm making an assumption, namely that, oh, you guys check this out, that my function is continuous over the closed interval from a to b. And if my function is continuous over the closed interval from a to b, what does the extreme value theorem tell me? Ooh, the extreme value theorem.
Which one's that?
Well, I'm sorry, say one more time.
I was guessing that there must be a local maximum.
See, I think there's got to be an absolute max or an absolute min. I think the extreme value theorem told us, when we saw this last, that over some closed interval from a to b, I'll always attain a max and I'll always attain an absolute min over that closed interval. So I think, by the extreme value theorem, f attains a max over the interval from a to b. You don't mind it to be at the endpoints. Isn't that how you found absolute max and absolute mins anyways? You evaluate your function at the endpoints, that closed interval, and you evaluate your function at any critical number in between. However, you guys think about this for a minute. If I'm going to attain an absolute max over this closed interval, but there's a value of x that's bigger than f of a and f of b over the corresponding open interval, then I think by both my asterisk and, how about my double asterisk? My double asterisk was this constraint relationship. I think f attains a max at x equals c, which is strictly between a and b, not including the endpoints. However, you and I have already taken some time in class proving Fermat's theorem that says this. If I attain a max or min over some interval, then it's certainly going to be the case that the max or min is going to have a derivative which is equal to 0. Well, if the function is differentiable. And since f is indeed differentiable over this open interval, then by Fermat's theorem, it's got to be the case that f prime of c is indeed equal to 0. We've just proven Rolle's theorem. Yeah, you know, maybe it is a case that this isn't some ground-shattering theorem in terms of you using it every day in practice in mathematics, but it's going to allow me to make a really nice, sophisticated jump. You guys, everything okay on the board so far so I can use my ruler? All right, if it is, I want to change my picture. Here's something so much more powerful. Again, some people think of calculus as a sequence of about 5 theorems, at least differential calculus. What's coming next is one of the big 5. So important, I'll give it a name. I'm going to refer to this as a mean value theorem. Does mean angry, mean in terms of average is what we're suggesting. Oh, you guys, this is beautiful. So, very much like my setup with Rolle's theorem, say about this? Just panic, say something about this fraction. What does it represent in my picture? It sounds very algebraic. What does it mean in terms of picture?
It's a rational average.
Thank you. It's an average y values, isn't it? It's the average of the y values over the interval from A to B. Actually, I can also think of it as the slope of that red line, can't I? Oh, sorry, did I misspeak? Is that a tangent line? No, but it is a secant line. It's not a tangent line because it doesn't touch my curve at a single point. Locally speaking, it's staying on one side of it. But it is a secant line passed through these 2 points of my curve. So, everybody, if f is continuous over the entire interval from A to B and differentiable over the corresponding open interval from A to B, then I think, intuitively speaking, there must exist some value of x called c in the corresponding open interval from A to B, such that when you look at the slope of the tangent line to the curve at x equals c, you're going to get nothing more than the slope of that secant line passed through the 2 points that we mentioned earlier. So you guys, with my blue pen, let me come in and try to find a point at which the slope of the tangent line is the same as the slope of that red secant line. Does that look like it might do? And according to my picture, it certainly seems to occur at a value of x somewhere between A and B. That's the punchline of the mean value theorem. Now notice that both with the Rolle's theorem and with the mean value theorem, they are indeed existence theorems. They tell me that these values for x called c do indeed exist, but they give me no algorithm whatsoever to actually construct that constant. I can sometimes, but as a general rule, that's not the point of these theorems. They are merely existence theorems.
Does it matter that the red line crosses that function at 3 points?
Completely irrelevant. Besides, I just concentrate what the heck is going on between A and B. So be it that this might be somewhat sinusoidal or something like that, and I cross it infinitely many times elsewhere. It's completely irrelevant.
Would you be able to say that A is that other lower point we're crossing?
Absolutely. And if I chose to move A over here, the conclusion's still true. It's just that in that particular case, it has to be true more than once, doesn't it? These theorems don't say that it's only going to be true for one such value of x we call c. It can be true for multiple choices. You guys, this isn't Math B anymore, so I need you guys to be well exposed to mathematical proofs. I'm afraid I am going to take another break and prove this theorem for you.
Wait, just really quick, how come it has to be continuous over the interval from A to B inclusive, but then when it's differentiable, it's exclusive?
So, Nabil, if my picture looked a little bit different, and the curve actually had an abrupt change, sorry, I have to do that black, hold on. What if my curve didn't do that, but did this? Now, I confess, I'm not actually differentiable at x equals b, because I've got a corner point there. But I think it doesn't change the result of the theorem. I think the conclusion's still true. So I don't really care about differentiability at the endpoints. I just need to make sure I don't have this abrupt change in directions on the interior of the interval from A to B. So Nabil, do you see how I showed you I'm not differentiable at that endpoint? But I think the conclusion still holds. So everybody, let's try a mathematical proof. Can I show you what I'm really going to do? I'm going to build a whole new function whose output is a vertical deviation between my black curve and that green secant line. I'm going to build a whole new function I'll call it h, whose output is nothing more than the difference in the output of my function f and the y values on the blue secant line. And then,
Blue our tangent line or secant line?
can you see one more time? I'm sorry.
I thought our blue line was our tangent line or our secant line.
Oh, you're right. I got the wrong color, don't I? My goodness. color blindness set in. And then we will use Rolle's theorem. I might have to check the three conditions are met, but we will use Rolle's theorem. So you guys ready? Because here I go. I think when it comes to secant line, I think it's merely going to look like a y minus y1 being equal to m times x minus x1. You guys, it's just math B business, isn't it? It's just that when x is equal to a, my corresponding y value is f of a. And if you take a peek at that, I'm going to make sure I get the color straight. If you take a peek at the red secant line, don't you guys agree its slope can be interpreted this way? Oh shoot, I lost my last factor. Is that an x minus a? So I think the y values on my secant line can be determined by just looking at an f of a and adding to that this fraction times x minus a. In that being the case, I think the output for my function h is going to be nothing more than my f of x's minus the y values of my tangent line, excuse me, I said tangent line, I meant the y values of my red secant line, which are nothing more than my f of a, plus my fraction times my x minus a. And now you guys that have created this function h, which is just a vertical function which outputs the vertical deviation between the curve and the secant line in red. Let's see if the three criteria in Rolle's theorem are being met. Let's check the first criteria. Is h continuous over this interval? Anybody? David?
Well, not if b equals a.
You know, you've got a good point. It's just that way back in Math D, whenever I used interval notation, it was always understood that A is strictly less than B. Otherwise, it wouldn't be an interval. I wouldn't be using this interval notation.
Oh, God.
So, do you guys think H is continuous? Ah, no bubbles.
Did you mean to subtract the fraction?
Yes, I did, because David watched. I was trying to create a function h whose output is a difference in the y values on the secant line, f of x. You guys, I was hoping you'd say trivially, yes, look, I've already assumed that was continuous over the interval. And that's just the y values on a line, which is continuous everywhere. And so I think the difference in two continuous functions is continuous. Clearly, that particular criteria of Rolle's theorem holds true. Do you think h is differentiable over the corresponding open interval? I'm hoping you're nodding your head fast. Again, I just got a whole new function h, which is defined to be the difference in two other functions which are clearly differentiable over the same interval. Well, mine's differentiable everywhere, but my f is already assumed to be differentiable over the open interval. And I think the difference in two differentiable functions is clearly differentiable. As a matter of fact, I can even tell you what the derivative function is. In fact, I think my h prime of x, if you guys look carefully up here, I think it's just simply f prime of x minus 1. Say it one more time. Minus f of b minus f of a all over.
Oh, because that's the...
Well, that's just a constant, it's true of 0. This constant times x has derivative, which is just a coefficient, a constant. And this constant has derivative 0 again. It's gone. Wow, you guys, I just checked very quickly that these two criteria are being met with by Rolle's theorem, or in Rolle's theorem. Let's see if the third criteria is being met. Let's see what f of a is. I misspoke. Everybody, I really misspoke. I meant to say, let's see what h of a is with this whole new function. So you ready? When I plug a in for h, a in for x, excuse me, don't I get an f of a minus f of a? Minus f of b minus f of a all over b minus a times a minus a. But isn't this just simply 0 minus 0, which is just 0? And when I take a peek at h of b, I think what I get is I have no clue. Is that an f of b? Minus f of a? Minus my nifty little fraction here. All over b minus a times
B minus A.
well, shoot, these b minus a's cancel. Now I'm left with one thing minus itself twice. Isn't that just simply going to give me 0 again? Therefore, by Rolle's theorem, it is the case that there exists a value of x called c in the corresponding open interval from a to b, such that my f prime of c, or excuse me, my h prime of c is equal to 0. Well, let me rephrase that. Actually, you guys, remember I took a break a moment ago? I said, oh, here's a drift function. I really mean this beast is equal to 0 when x is equal to c. So I've got an f prime of c minus my f of b minus my f of a all over b minus a is equal to 0. Oh, but shoot, now when I add this fraction to both sides, doesn't that really tell me this? That f prime of c is equal to f of b minus f of a all over b minus a. I've proven what I wanted to show. So now we really must believe the mean value theorem's conclusion. But again, take this with a grain of salt. The mean value theorem conclusion simply says there exists a value of x, call it c, that does all this garbage in here, but doesn't tell you where it is. And I want you to appreciate the beauty behind the geometry in this particular theorem. Got a nice clean curve, clean meaning both continuous and differentiable over the appropriate interval. Then I think any secant line, or the secant line past those two endpoints, is going to have the quality. There's another value of x in between these two values of x here and here, for which the tangent line is parallel to that secant line. That, to me, is what this particular punchline says. Because this, to me, represents the slope of the secant line. This represents the slope of the tangent line. So, can we put this to a test? I know this theorem does not guarantee you can find a C every time, but if I'm careful enough in making up my examples, maybe it will be true that we can find C on occasions. Can I get rid of the left bit? So I can erase